those of you who know, I am a committer and I am a PPMC member today. Extra something I'm doing there, I have a master from Stanford and bachelor's from Berkeley. So thank you for everyone for coming to attend CloudStack Labs introductions and architecture. Today I'm going to start with the introduction, and actually I'm going to get very deep into CloudStack's networking, its architecture, plugins, and also the Apache process today. So as most of you probably know already, CloudStack is a software that builds IaaS clouds, that's infrastructure as a service. It allows an end user to create VMs, create disks as network and network services, and it allows them to do it self-service, as the administrator does not have to be involved. It is Java-based, it is very scalable. We have many vendors working with us to add in and support for different hardware and software and VM-based solutions. And we support both native and EC2 API. When we build CloudStack, we took a look at how Amazon actually builds their EC2 service. It starts with their commodity servers, added networking and commodity storage. They put open source and hypervisor on top of that. Added in their own orchestration software. Added the API for the developers. And then they added the e-commerce platform on top. So for CloudStack, we start with physical hardware, networking, servers, storage. For hypervisors, we support with ESX, AGS, KVM, Send Server, and Oracle VM, OVM in this case. And you add CloudStack's orchestration software on top of that hardware. And on top of that orchestration software is our own native API, or the AWS API. And then you can put a portal on top of that API. To provide the same functionalities as Amazon EC2 service. Citrix has a cloud portal software that you can put on, but that part is not part of the CloudStack software stack. A little bit of history about us. We started the company back in 2008. It released the first product in 2009. At that time, it was a closed source development. And in May of 2010, we open sourced with GPL v3 about 98% of our software. So I guess we call that open core. In August 2011, we open sourced 100% of our software. And in 2012, we contributed that code to the Apache software foundation. And so as a Apache project, we are currently in incubation phase. What that means is that it is not a top-level project. It is to be determined whether or not we will graduate to a top-level project. Under this incubation phase, we just released 4.0. That was earlier this week. Most of our infrastructure has been changed over to Apache's infrastructure. The bugs and wiki, mail list traffic, pretty much has been changed. And we today have quite a bit of non-Citrix contributors. When we first contributed, it was only Citrix. Today we have a lot of non-Citrix contributors, committers, and PPMC members. PPMC is the governing body to decide whether or not CloudStack will graduate to be a full-fledged project. And about half of the people on PPMC today is non-Citrix. And Apache has been great for CloudStack because ever since we contributed it back in April of 2012, the traffic for Apache has grown. As you can see on that green line there, it's been spiking up and settled down a little bit recently, but it's been doing well for CloudStack. So I'm going to go in a little bit on IaaS concepts that CloudStack has. So we've been doing this for about 3-something years, and we took a look at what people actually use the cloud for. When you go look at Amazon, Amazon Cloud is very much on the left, on the right-hand side either, and it's all about designing around big data and massive scale and next generation apps. But when we went and talked to a lot of our customers and a lot of our users, we realized actually a lot of people is using it for traditional server virtualization as well. And in that, then you are deploying basically traditional enterprise apps and client-server compute. So in the differences for traditional and cloud workload, when you deploy a traditional workload, even though it's in the cloud, you still the expectations are quite different. And in traditional workload, you expect reliability in the hardware. You back up everything, and there's high availability, there's fault tolerance, and then MIM controls the recovery. And so you have to think server virtualization in that case. And in the cloud workload, the applications themselves are designed for failure. The resources are said to be given real. That means that they can be gone at any time. And multi-site redundancy, and it is a self-service recovery. So the app can go away, and then another instance needs to come back. And that's up to the deployer of the app and not the administrator of the basin. So CloudStack is the one software that can actually embrace both of these types of workloads. You can control cloud area availability zones backed by object store, and you can also control traditional zones with VMware, with enterprise networking and enterprise storage, such as SAN and ISDS. And that's about basically the same type of deployment. You can deploy that under one single manager. So for CloudStack, to deploy our management servers, our management server can deploy in one availability zone. There needs to be a low latency connect between and the availability zones that it controls. But they can be geographically distributed. I think we have customers who deploy between Singapore and India, for example, and they're able to use CloudStack for one single CloudStack for that. And each single management server node can manage up to about 10K hosts, but you can cluster the management server nodes to handle more and also for dependency. And in the cloud area zone deployment, and CloudStacks, there will be multiple availability zones, and you will duplicate CloudStack onto a different availability zone. So when one availability zone goes down, then you can pick up the server in the standby zone for management server to pick up the traffic. But in the traditional zones, then you would need to have pretty much redundant everything. It is how you would set up an enterprise data center. Redundant routers, redundant hosts, storage. You're responsible for backup. Everything needs to be high quality. And this is a picture of CloudStack's management server, our internals. So in general, you start with our front end, which is our API layer. This API is able to directly access MySQL to grab any information that the end user needs. But when the end user files a job, then the front end would actually put the job into a job queue, which is picked up by orchestrators here for VM, network, and storage. And these orchestrators have all of our business logic. But when it needs to, inside that orchestration process, it needs to do provisioning of the actual hardware, then it sends that information down to a message bus. And it goes down to our agents. And some of our agents live within the management server. So for example, Send server, that agent is inside the management server. But KVM agents are remote from the management server. They connect using a TCP connection. And we have other agents that lies in the data path for CloudStack to manage template movement and console proxy access. And they all connect back to the management server. And the communication between them are async and RPC over JSON. And also, on top of that, we have a usage process, which takes the events generated from CloudStack and change them into usage records for building purposes. So while all of these guys are fitted into one management server, we have different web tools to take care of this work. So we can deploy as 3 different management servers in one. So this is a list of the functionalities that CloudStack supports with different hypervisors. For the Send server hypervisor, we support 5.6 all the way up to 6.02. And we support the open source cloud platform. Send cloud platform is very confusing because Citrix also has a cloud platform, which is CloudStack. Send cloud platform 1.1. And for Send servers, we support incremental snapshots. We use VHD as our primary template format. And we support pretty much all the storage mechanisms that Send server supports. For VMware, we support 4.1 and 5.0. We only support full snapshots at this time, so no incremental snapshots. We support VMDK as the file format, and we support pretty much everything that VMware supports as storage. For KVM, you can see that there is an agent on the KVM. That indicates that KVM has a remote agent deployed on every host. We support well 6.0 to 6.2, and as of 4.0 release, as Ubuntu 12.04 has been added. We support full snapshots in KVM, but it is not live. This means that when the VM is running, the snapshots are not crash consistent. We cannot guarantee that crash if they are current crash consistent. But that's a KVM problem in itself, not particular to CloudStack. The file format used is QCal2, and we support NFS, iSCSI, and Factor Channel. And I believe as of 4.0, we actually support Ceph. And we also have OVM support. For OVM, we support 2.2. There's no snapshots. We support only raw images at this point. There's support for NFS and iSCSI, but there is no storage over provision. And this is a kind of overview of our scalability. In production today, we have 30,000 hosts in our customers. We use our simulator to test the scale. It takes about 4 management servers to manage about 30,000 hosts. It really only takes about 3, but we take 1 more in case 1 fails. So 1 is really a hot scale. And we can scale to hundreds of thousands of hosts possible with multiple management server clusters. And that's the concept of regions, which is coming in the future version of our CloudStack. So I'm going to go into more detail about these particular graphs in the later slide. So for features in CloudStack, we are basically vendor agnostic. We support pretty much all the hypervisors out there. Hyper-V is being developed right now. And we even support Vimeo as a as a hypervisor. And then for storage, we support fiber channel NFS. I think we went over these before. And we also support object storage for our secondary storage. For network, we have multiple network types. Layer 2 guest networks, layer 3, AWS style networking, and we support various isolation runs. Today, the one that is used most often is VLAN, but other people have been adding in VLANs, OVS support, and Nicera support. Firewalls, load balancers, VPN, and other network services. So, I mean, this is basically what we do. We allow the end user to go in and on top of this layer and do self-service VM operations. You can start, stop, restart, destroy. Once they start a VM, they can have console access to the VM. That's provided by CloudStack. And they can monitor their VM status, look at their CPU, look at how much they're using the network. And then they can scale their VMs depending on the need. So if 2 CPU and 1 GB is not enough, you can upgrade the VM, and then we deploy with a higher offering. And we also manage snapshots and volumes. We can add the delete volumes. We can attach them to attach and detach them to the VMs. You can create templates for the volumes, which allow you to create a VM template, and then we deploy that as a separate VM. We can also schedule snapshots as we support hourly, daily, weekly, monthly intervals. And we can look at your snapshot history. What we do is we package all these things and the different parameters and capacities into service offerings. So then the administrator can present that to the end users in one single package. So for compute, you can specify the CPU and how much speed and memory. And you can also specify the host tags. As host tag with the CloudStack is a way for you to specify that this particular VM needs to go onto a certain host. We do matching between the tags, and if they are equal, then it's placeable on a certain host. You can enable the HA capabilities of that VM, and you can cap the CPU for a particular VM. For disk, you can specify the size. You can also specify tags. This is a way to do storage class of service, right? You can tag the storage and says, this is I want to be SSD only, and then you can actually tag the storage pool and says, this storage pool has SSD, and we will only match VM's volumes onto that particular storage pool. And on network, there are similar parameters that you can set. Network rates, we can set virtual router to be redundant, and there is a firewall. You can choose the firewall that you want to offer to the end user. Today we have a virtual router, and we also support SRX. And you can also choose the load balancer that you offer to the end user. But when you do this, the end user only sees one particular thing. They do not see all these options. These are configurable by the administrators. And by default, CloudStack is a multi-tenant software. It understands that there may be different groups of people that you're putting in, and we allow you to specify domains and subdomains within domains. And this is basically a support for a reseller model, where an administrator or a cloud operator allows people to resell virtual machines underneath. And each domain can have subdomains, and the domains can also have accounts. And accounts then would have a bunch of users. And you can set limits at various stages. You can set limits as to the number of VMs a reseller can actually deploy in your system, or you can set it at the account level as So for network and network services, as we look at public IPs, is for NAT and load balancing, and we control the traffic by using ingress and egress firewall rules, and we set up rules to do load balancing traffic between different VMs. And we package that into a network offering and for the administrator, and the administrator specifies that and offers that to the end user. And these are the type of networks that we actually support. I will go into that a little bit more in detail in the networking section of this, but this is an overview. We support layer 3 guest networking, and this is pretty much like Amazon's network, where everybody actually is on the same network segment, but is isolated from each other by using security groups. And then and network services are managed by CloudStack. So under the same network group, you can actually place a physical load balancer, for example, like the Netscaler, and provide VIP and ELB services. We also support the layer 2 guest networking, and in this case, then all the guest networks are isolated by VLAN, and they can specify their own IP address scheme. And when they need to go out to the public internet, they will go through CloudStack's virtual router. But at the same time, if the administrator believes that the virtual router is not performant enough, they can switch it over to using a hardware firewall like the SRX, or use physical load balancers for such as Netscaler FI. Here's a comparison of the layer 2 and layer 3 services. For isolation, for layer 2, we use VLAN and SDN. And layer 3, we use security groups. The performance is pretty close between the two. For the network setup, though, it's much easier to set up the layer 3 because it's a flat network. You don't have to deal with VLANs and trunking VLANs. And if you were setting up for using using VLAN, and then it's actually a very moderate complexity to that setup. You have to understand the switch level of changes. But in layer 2, it supports broadcast, but layer 3 does not. Scalability-wise, it's very good for layer 2, but there is a limitation for VLAN. And for layer 3, we've done pretty well. Our biggest productions is on layer 3. And interoperability with physical servers. So the problem here is that what the physical hypervisor supports, and pretty much everyone supports VLAN. That's standard technology. But layer 3 today, the support is only at SAN server and KVM. And so for CloudStack storage, there is primary storage, and primary storage is the storage where the VM actually runs the disk side. And so for primary storage, the biggest cost there is, or the biggest measure there is the IOPS, right? Because you can have a number of VMs running there, and they all need to be very performant. So generally, primary storage is more expensive. We support local disk, iSCSI, fiber channel, and NFS there. And like I said, SEP for KVM has been added for 4.0. For secondary storage, that is the storage for templates, ISOs, and snapshots. The measure there is generally capacity of secondary storage, because snapshots can grow very quickly, and as it grows, then capacity of the secondary storage needs to catch up. So we support secondary storage at its own level, but you can have multiple secondary storage. And we support NFS, OpenStack Swift, and others are coming in later releases. Okay. So that's the current functionalities of CloudStack. this is a slide that I did for in Beijing Cloud Expo, and it details the CloudStack's architecture. So I think this I covered in the introduction, whereas we allow self-service access to CloudStack's UI. And when you deploy CloudStack, you start with the hypervisor host, primary storage to those hosts. And when you group them together, then that grouping is called cluster in CloudStack. When you group the clusters together, then it's called pod in CloudStack. Pods are linked by layer 3 networking, and you add a secondary storage. That entire grouping will be called a zone in CloudStack, and the management server farm will be able to manage multiple availability zones. So I'm going to skip over this slide because it's the same slide as the one about storage support. So when you deploy CloudStack, take one particular zone for example. You start with hypervisors, as I said, form a cluster, and then you form primary storage. You attach primary storage to them, and you attach them via layer 2 networking, and multiple clusters into a pod, and multiple pods into the secondary storage, and all of that gets linked in with a layer 3 storage. And then you duplicate this zone multiple times to achieve multiple to achieve redundancy in the system. For the management server, you can deploy multiple management servers in the cluster. It will be on the same MySQL, and you replicate it for backup. And you place a load balancer in front of the management servers to take the user API and admin APIs. I request this. So CloudStack is CloudStack needs to is structured to manage complexity, and we have what we call the 3 C's of complexity. One is control, another is choice, and the third is compliance. And let me show you what I mean. And so this is the same picture as before, right? We allow end users to have access, self-service access to VM and infrastructure underneath. But then, and that starts off as a very simple proposition. But then underneath, if you want to give choices to the administrators, because they like to have different choices about the hardware that they deploy. And you need to be able to provide all those because they're familiar with different vendors that they work with. And on top, you need to provide control and compliance. And so you have to be able to have ACL, access control. You put in limits as on what they can do with the VMs, how many VMs that they can deploy. And then you have to add in different ways of doing governance. For example, a lot of cloud operators do not allow you to destroy the actual volumes. When the user says destroy, they need to keep it. They need to retain it for 30 days before they can actually destroy the volume. So we need to add in that type of governance measures into CloudStack. So when you have all 3 of these, then CloudStack becomes very complicated because there's actually quite a few things that you have to manage. Okay. And again, this is the networking that CloudStack supports, layer 2 networking. And as you can see here, in layer 2 networking, the guest VMs have the same IP addresses, but they cannot see each other because they are isolated by VLAN. And in order to allow, or to even visit each other's VMs, they have to go through a virtual router, go up, and then come back the other virtual router to visit guest 1's VM, visiting guest 2's VMs has to go through that box. They cannot actually directly see each other. And this is a typical multi-tier networking network that a web app would deploy. You have the web VMs, in the middle, backed by load balancers and firewalls. Behind them is the application tier, and behind them is the DB tier. And you want to isolate them. So in CloudStack 3.x, what we support is the ability to plug these VMs into multiple networks, so that they themselves are isolated, but they can still reach, the web tier can still reach active, and active can still reach DB. And each one of them is protected by a virtual router. In 4.0, CloudStack actually supports the concept of VPC. So in here, this is the same application with the web tier, app tier, and DB tier. They are all on their own network segments, and then switching between these segments is protected by our virtual router. Our virtual router actually does the actual switching, and you can place firewall rules to protect between the networks. And of course, you can also place load balancer onto this, as that goes directly to the web VMs. And we support other topologies, right? Here's one particular topology where there is absolutely no network services. You do not allow them to go out. So for example, you're running a Hadoop instance where you're doing just computation, and you do not monitor anyone from the outside to access any of these instances. You do not provide public IP access, and you can only access these through a console proxy. And that's how you can actually secure it in the best kind of method. We also support dedicated VLAN, and so a user can specifically say what the IP address of the VM is. And we support the idea of having MPLS connection back to the data center, the user's data center, to hook up their virtual networks with the data center's networks. And then there's also shared VLAN, which is the ability to say an administrator can create a particular network and then put all the end user's VMs on that network and isolate it through other means that user VMs. And we support the Amazon style layer 3 networking. And in this case, it's the web VMs and DB VMs comes up. But then you place them, each one will have a firewall in front of it, and then you place them in different security groups. So the DB VMs will be in the DB security group, web VMs will be in web security group, and then you allow the two security groups to reach each other. And in that case, then you protect, you do not allow other users, web VMs, to reach into this web VM, into this web security group, but the web security group is linked to the DB security group. Let's take a look at CloudStack software architecture. So what you see here at the top is the different clients that CloudStack has. There's the CloudStack's own UI. There is Cloud Portal, which is a product from Citrix. You can also access it through CLI. And for post 4.0, someone has actually improved our CLI significantly, and so something good to try. And you can also use other clients and other vendors who support our API. Inside the management server, you will start off with our orchestration engine, and inside here, it drives the orchestration processes for CloudStack in terms of deploying VM, attaching a volume, things like that. It also syncs between the resource and the management server, so that they can report any changes of VMs that is at the actual physical resource. And it generates events, which then gets consumed by the usage server over here. And when the orchestration engine decides it needs to use it needs to provision the actual physical resource. Then it will call into the plugin APIs. The plugin APIs allow other people to plug in their hardware and their control software so that they can provision volumes, provision network without CloudStack norm. CloudStack only orchestrates within the CloudStack entities. And when these things needs to contact the actual physical resource, then it will reach to send messages over our message bus, and it goes down to our resource layer. Our resource layer is our actual translation layer. For example, if you want to talk to a SEND server, the SEND server SAPI API is translated between CloudStack VM and the SEND server's VM. Same thing with VMware and KVM, and same thing with the network rules. And another purpose of the resource layer is that the resources are deployed into the data paths of CloudStack. So say, for example, you want to transport templates between two particular zones. You can either transport them within management server, right? But then management server is the control plane. Its scale is very different than how our template transfer should happen. So what CloudStack does is it raises up a VM. That VM contains a resource for transporting the templates, and then that VM takes over transporting the resources, because then it is in the data path. And management server will only stay in the control path. In order to access those, we go over our message bus, which we said earlier is RPC, and the file format is JSON. And on top of the orchestration layer, here, these are the additional services that we provide, things that manages and do automation for CloudStack. Things that says, oh, in order to do so-and-so task, there's more than one step in the orchestration, and it does these automations for the administrator. And I will go into them a little further later. And between this API and the REST API is basically our ACL access, and that's where all our governance and control for the administrator goes in. And the lower layer is basically our framework for being able to cluster together management servers, for accessing the message bus, for accessing the database. So as I said, orchestration engine understands how to orchestrate long-running processes. VM starts, snapshots, template propagation, things like that. It follows well-defined process steps, and then it calls the plugin API to provision the actual work. For the plugins, and it is basically various ways to add capabilities to CloudStack. If you want to add another network element, let's say a load balancer for Bouquet, then you will write a plugin that understands how to manage Bouquet. When CloudStack does orchestration, it will say a VM has come into this network, and it will tell the plugin. And the plugin then can provision the VM for the load balancer for Bouquet. We have very clearly defined interfaces for those plugins, and the operations for the plugins must be idempotent. That means it has to be repeatable, and all calls are at transaction boundaries. That means CloudStack ends its database transactions when it calls these plugins, because it's very likely that all these plugins are actually doing long-running operations. You're contacting F5, you're contacting SRS. When you're programming, it can take up to 30 seconds. So we end all our transaction boundaries. So we do not allow people to do rollbacks in the database to enforce the atomicity of the operations. And you have to handle that yourself. And you should only compile against the API module. And this is an analogy of the plugin. And so it can be two jars. one job will be deployed into management server, and that is where the business logic will go. This job basically controls how it's going to go talk to its own resource, how it's going to program, and for example, things such as whether or not it's deployed as a HA configuration, and also how it does its own resource management. So in this job, it can actually implement multiple plugin APIs, and then it can expose a REST API through CloudStack so that the administrator can actually configure that plugin, and it can have its own data access layer. So one example is the OBS plugin, which implements both the network guru interface and the network element interface. And I'll go into that a little bit later about what each of these interfaces do. And then if you need to execute certain things on the resource, then you will also provide a server resource job that actually is deployed co-located with the resource. And they communicate with each other, but when it needs to have things in the data path, or when it needs to do the translation, then the plugin will communicate with the server resource to execute what it needs. And that is defined by your own code. CloudStack will not do it. So these are the plugin interfaces available. These are basically defining what CloudStack needs from the plugins. There's Network Guru. Network Guru is a definition of what the network should look like, what isolation method it should use, what is the IP address scheme that you want to use. So in CloudStack, when we go to the network, what we do is go to the Network Guru and says, well, we need a network. We don't know how to provision it on the actual hardware. You need to help us do that. The network guru will return back and says, you should be using this particular VLAN, you should be using this particular set of IP addresses, and CloudStack will follow that. Once we have that, then CloudStack will inform all of the network elements and that is in that particular network, and says, we are starting up this network. It has to be provisioned with this particular VLAN. It has to be provisioned with these IP addresses. If you need to adjust your own hardware to work with this network, then you need to go adjust them now because it's about to come into use. So network element is the interface to do network services with CloudStack. These services include DNS, DHCP, load balancing, VPN, port forwarding, and a myriad of other things that we've been adding. And deployment planner is a plugin that you can write to decide where the VMs are going to go. You can use heuristics. We've implemented heuristics that says a particular user's VM should be all concentrated on one particular hypervisor or one particular cluster. Or you can decide that all that user's VMs should be dispersed across all of the resources, so that it gets dispersed between different pods and different clusters, so that if one host goes down, all of the users' VMs will not go down. So a deployment planner is where all of these heuristics can go in. You can specify the deployment planner to be deployed with CloudStack, and there will be changes in the future to allow you to specify the deployment planner to use when you deploy a certain VM. Investigator and Fencer are two plugins that people put in to enhance the HA process in CloudStack. We need to be able to tell whether or not a VM actually has gone. A VM is actually down or host is actually down. And people can write adapters for that. For example, if you have IPMI in the system, you might be able to detect that the host is actually down much better than CloudStack. So you can write an adapter or a plugin, put it into CloudStack, and when CloudStack asks you to investigate, then you can return back and says, yes, it is down. And CloudStack will use that information to pursue its high availability data process. There's the user authenticator plugin that allows you to do different ways to authenticate the users. There's a security checker plugin that allows you to specify that I want to do my ACL in this particular fashion, not the one that CloudStack has. And there is a host allocator and storage pool allocator plugins. And these plugins are specific to the capabilities of the hypervisor and the storage pool, because different hypervisors may have different ways to determine whether or not a VM can be allocated to that hypervisor. So when the deployment planner using heuristics says, I want to deploy to this set of cluster, this particular cluster of hosts, then we will go ask the host allocator and say, can you find me a host that can actually deploy this VM? And we will ask the storage pool allocator and says, can you find me a storage pool that can hold the volumes for this particular VM? So there's a lot of different ways to adapt CloudStack. Storage pool, host allocator, storage pool allocator, and deployment planner is the best places when you put in algorithms to adapt CloudStack. And network elements and network glue is when you put in and code to add different hardware support into CloudStack. And CloudStack is and I brought this up a little bit earlier. CloudStack is very important for CloudStack to separate the data path and control path, because data paths in general in a data center is much higher bandwidth than control. So earlier in the introduction, I showed that CloudStack's deployment starts off with a front end, and when the front end receives a request to do a certain action in CloudStack, it actually files that into the job queue, and then something else will bring up the job and executes that job. So this is the first phase of that access. And here, the end user API receives a deploy VM call. That process that thread will go through the ACL checks. Will allocate all the entities necessary in CloudStack. So it will call our user VM manager and says, oh, I allocate this particular VM. The user VM manager, which is the VM orchestrator, would then call the network orchestrator or virtual. The user VM manager will talk to our virtual machine manager, because we actually deploy multiple types of virtual machines. So the user VM manager is not the same thing as a virtual machine manager. And the user VM manager will call the virtual machine manager and says, oh, I need to allocate a VM. Who then will talk to the network manager, which is our network orchestration, and says, you need to allocate a NIC for this particular VM. And then, as I said, for network manager, it turns around and says, hey, the network group, you need to tell me what IP I can give to this VM. Network manager itself doesn't understand, because it doesn't understand IP addressing scheme in the network that the VM is about to go in. So it will contact the appropriate network group and says, you need to give me an IP for this particular VM. And once that's done, then the virtual machine manager will talk to the storage manager and says, you need to allocate me a volume. And all of this allocation right now is only happening in the databases for CloudStack. None of it is provisioned. And once all of those entities have been set up in our database, then the end user API will schedule a deployment job. And then it returns with the job ID and the VM ID. The end user will keep querying the job to see if this job has been completed. Now, this job has been scheduled into the job queue, and a different process will actually pick up that particular job. Now, the actual provisioning and orchestration of CloudStack happens. Right? So the job queue says, oh, the job is to start the VM. Right? It already created the VM. It created the VM in here, in the CloudStack database. And now it says I need to go start that particular VM. And it comes down to CloudStack asks user VM and says start this user VM. And the user VM manager again says to the virtual machine manager, you need to start this VM. So the difference between these two steps is that in here, there are information about the user VM that's important. Whereas here, we're orchestrating against all VMs. There's to us, a virtual router and a user VM at this level to this virtual machine manager there's no difference. They all start the same way. And the first thing that the virtual machine manager does is it gets the deployment path. And from the deployment path, remember in the plugins, I've said that the deployment pattern uses heuristics to determine where to place a VM and its storage. And that deployment pattern gets returned to virtual machine manager. Virtual machine manager then talks to the network manager and says, you need to prepare the NICs for that particular VM. Now the VM may be placed in multiple networks, or it may be placed in one. But it wouldn't matter because to CloudStack, we just go through each network and says, well, which network does the VM needs to be placed in? And each one we will create a NIC and says, you need to reserve the resources for that particular NIC. So the network manager then talks again to the network group because again, the network manager is orchestration only. It does not understand what is the IP addresses that the NIC should be on. Well, it does not understand the gateway that the NIC should be on. What it does is it says, I understand I need to go get that from the network group at this stage because I need orchestration. And then it notifies the NIC. And then once the network guru comes back and says, yes, I have all the resources ready for you for this NIC. Here are the resources. It might be this IP address with this gateway and on this VM. Then the network manager will inform all of the network elements that is in that network and says, hey, this VM is about to start. It will be on this particular IP address. If you need to do something about how to configure it to your load balancer or your DNS server, then you need to do it right now so that the VM can start. And the network elements will make agent calls to their resource. So here is the difference. When I was going over the anatomy of a plugin, I was saying, one part of the plugin needs to go into the management server, and one part of the plugin may be co-located with the resource. So here's the difference. This network element plugin and is inside CloudStack to drive its control. It might say, this particular VM is on load balancer A. CloudStack doesn't understand that. CloudStack only says, there's someone, it needs to do load balancing. But it doesn't understand which instance of the load balancer is on. That control is left to this particular plugin. And it makes its own call to that particular load balancer and says, hey, I need to add this VM into the load balancer. And once all the network element comes back and says, yeah, it's okay, we've prepared everything for this particular VM to be started in the network, then the virtual machine manager comes back and everything gets returned to virtual machine manager, and virtual machine manager proceeds to prepare the volumes. And it calls the storage orchestrator to do that, which is our storage manager. And the storage manager will say, look, here's my orchestration steps. In order for me to start the VM on that particular storage, I need to first make sure his template is on there. And then I also need to start create the volume on that particular primary storage. So the storage manager will call the template manager and says, move the template onto this storage, primary storage. That results in an agent call to another server resource. This is not the same resource as the network resource. It calls a different resource and says, oh, you need to make the copy of the volume over, and then create the volume on that particular primary storage. And when that's all done, then the virtual machine manager will make a call to its own resource. And that's different from the previous two. This is to the hypervisor resource and says, start the VM. I have all the information ready for you to go. and the resource would then take that information and start the VM. Once that's done, that returns back to the job thread. The job thread will store the job results into the database. And then at this point, then the job status for that VM start will be complete. So this is a sequence diagram for how we start VMs. We follow very similar things for starting VMs, attaching volumes, detaching volumes, doing snapshots, things like that. So the design goals for CloudStack was that we need to design for the complexity, right? There's control, choice, giving choice to the operator, giving control to the operator, and giving compliance to the operator. We have to design for scalability because the number of resources that we have to deal with is very high, and we do that by separating out the data path and control paths, and then we do that by maximizing the use of the database connections. And then we have to design against failure. So here we have to be able to provide very clear boundaries of what CloudStack does and what provisioning does, and allow the administrator to go and figure out what happened on failure. Because in our experience on failure, if we keep doing the same thing over, oftentimes it actually makes the situation worse than better. So you can do more information. So should we take our first break here?